In our notes today, we're going to be talking about section 7.2, dividing rational expressions and extending on what we did in our previous sections. You're going to have to be judging when you're working on our problems today, but realizing first, when you have two numbers that have the same root, you are allowed to either multiply them together or divide them, and you can either write them as a single fraction, as we have in the second part over here, or in a double fraction where you have the root of n over the root of b, and we break that up into two parts. So let's take a look at our first one, and we're going to either divide or simplify, or we're going to simplify and divide, and we're going to have to make some good judgment calls on that. So the first question really is, does 243 divide evenly by 27? And in this case, because it does simplify easily to 9, then the square root of that is 3. Now, you could have rationalized the denominator and all those kinds of things, but I want to encourage you to really try hard to make sure you're doing the easy processes first. Second, we've got the square root of 12, x to the fourth, over the square root of 3x. Let's see if we can simplify first. Well, the 12 and the 3 cancel to a 4. The x to the fourth and the x cancel to an x cubed. Now we do have a square root, so we're going to break this into a perfect square, and what's left over, so that's 4x squared with a leftover x at the back end, just like normal. And that's going to leave us a conclusion of 2x on the outside of the radical with the square root of x on the inside as our leftover part that we drag along. Our third example, we've got 192 divided by 3, and 192 divided by 3 is 64. So we've got the cubed root of 64, and then we've got x to the 8th divided by x. That leaves us with x to the 7th. So in this case, we're going to try to say, hey, we need to break this into a perfect cube, and then what is perfect cube is left over? Well, 64, as you know, is a perfect cube. It is 4 cubed, and x to the 6th is the perfect cube right below x to the 7th, leaving us with one single x left under the radical sign. We now take the square root, which would give us a 4, divide the x to the 6th in by 3, and we get x squared with a leftover cubed root of x. So in each of these first three, we've just very simply simplified first and by dividing, and then we did the simplifying of the radical signs. That's not always the case. There might be some other things that we need to do later, and that is going to be called rationalizing the denominator. As we look at rationalizing the denominator, we need to understand that rationalizing, once again, means you must get the radical out of the denominator. We did this before last week as we practiced getting a radical out of the denominator using conjugates. Well, here we don't have a binomial on the bottom, we just have the square root of 5. It would be nice to have the square root of 25 in the denominator, because if we had the square root of 25, that would be a perfect square, which would lead us to a bottom denominator of 5. So, to get the square root of 5 to become the square root of 25, we're merely going to multiply top and bottom by the same square root, which is the square root of 5. Whatever we do to the bottom, we do to the top, so the top becomes the square root of 15, and so my answer is the square root of 15 over 5. Please note that these two do not cancel, as one is inside the square root and one is outside the square root. On B, we have a problem where we have the square root of 8x in the denominator. So we're going to have to multiply by something. Well, we have to think to ourselves, what would we want to have in the denominator? Well, we'd like to have a perfect square, like 16. We'd like to have an x squared, because both of those will give us a square root that is easy to deal with, giving us 4x. So what do we need to multiply by to get that 16x squared? Well, we multiply by square root of 2x and square root of 2x. So the numerator becomes the square root of 10x, and we have the square root of 10x over 4x as our answer. So let's summarize this at our left-hand side, or our right-hand side here. If we're going to rationalize, we reduce if possible, and then we're going to multiply the top or the bottom by a number or a variable, or both, to make the denominator a perfect square or a perfect cube. So once again down here we have a 12x. Our target is 36x squared, so we're going to multiply by a missing 3x on the top and the bottom, and that's going to give us 15x square root over 6x. Remember, that our 15 and our 6x do not cancel because one is inside and one is outside. Let's keep looking at some examples down here on our second page. We have x to the fifth over 3x squared y. Well, the first step in this problem is going to be to reduce as much as possible. So we're going to cancel two of those x's and leave x cubed on the numerator. In the denominator, we're going to have the square root of 3y because all of our x is canceled. So that means in the denominator, we're going to have to rationalize that 3y. It sure would be nice to have a 9y squared in the denominator. To get a 9y squared in the denominator, that means we're going to multiply the top and bottom by another square root of 3y. So that's going to give us the square root of 3x cubed y over 9y squared. Now, here we've got a little bit of a unique situation because we need to keep going in the numerator. We'll come back to that in a second, but realize the bottom is just going to become 3y. The perfect squares that go in 3x cubed y is an x squared. What's left over is 1 3, 1x, and 1y. So let's see what this leads us to. The x squared comes out as an x, leaving us with the square root of 3xy all over 3y. So we have two things going on in this problem C. We're rationalizing the denominator, and then we're simplifying the numerator after it's been rationalized. This is going to happen in some cases, but not all of them. Let's look at letter D. On letter D, we have a cubed root, and this is the only example we have of cubed root. It's not really that different. We just need to make sure that when we finish our problem, we're going to have a perfect cube on the bottom that relates to 4. Well, I think you'd realize that 8 is the first perfect cube that is a multiple up by 4, and y to the third is a perfect cube coming up from a single y. So now we have to say, what do we need to multiply by what's missing? 4 times what is 8? 2, y times what is y cubed? Y squared. And so we're going to multiply the top and the bottom by 2y squared. That's going to give us a numerator of 10y squared. What does that give us as a result? The cubed root of 10y squared over 2y. Now we look at our numerator and say, hey, does anything come out of there in terms of perfect cubes? The answer is no, so in this case we're all done. Our last one here with letter E is going to give us a situation where we have a binomial in the numerator and a monomial in the denominator. But once again, we're going to shoot to have a perfect square such as 25 in the denominator. What are we going to multiply by? The square root of 5 over the square root of 5. Be careful to put parentheses on the top because you're going to have 2 parts times that square root of 5. What does that give us in the numerator? Well, that gives us 2 square roots of 5 plus the square root of 25 when we distribute. Let's keep going on this. That'll give us 2 square roots of 5 in the numerator plus 5 over 5. Now, this is a case where we want to take a look, and we look at this 2, that 5, and that 5, and if all 3 of them divide by the same number, we can simplify. But in this case, we can't. Our last example involves rationalizing the denominator and reviewing some of the ideas that we talked about in our last section. In order to get rid of a radical in the denominator that's a binomial, if you remember, we need to multiply by what's called the conjugate. And the conjugate will be the square root of 5 plus 1, which is exactly what we need to knock out that radical. So let's multiply the numerator by that same conjugate. Multiplying the numerator, we get the square root of 25. Outside is the square root of 5. Inside is 3 square roots of 5 plus 3, all divided by the denominator. Now, what's amazing about the conjugates in the denominator, remember, is the middle terms drop out. And I'm going to multiply this out for us just so we see it. Minus 1 square root of 5 minus 1. Simplifying the numerator, we get 5 plus, realize this is a 1 square root of 5, 4 square roots of 5 plus 3. Our denominator, we have 5 minus 1. We're going to bring this up here. That gives us 8 plus 4 square roots of 5 over 4. Let's analyze once again. And we see the 8, we see the 4, and we see the 4. Here's the first case where we have a situation where you can divide all three of these by the same number. That number that we can divide by is 4, giving us 2 plus 1 squared of 5. We don't need to write that 1, so that is our answer. We're going to have some problems on our homework tonight involving rationalizing denominators and some rationalizing when we have binomials in the denominator, as you can see down here. I hope this has been helpful in understanding best how we can divide radical expressions effectively when we're working with fractions.